David Woodruff and his group for inviting us to have a workshop on randomized numerical linear algebra and applications. I would also like to thank, of course, my co-organizers, Ken Clarkson, Pratik Jain, and Michael Mahoney for helping put together this workshop. And I have a rather long introduction talking about stuff that I assume most of you have already seen more than once, but I wanted to bring everybody sort of up to speed with respect to the workshop. We're going to have a lot of talks discussing more advanced, more state-of-the-art results in the next 4 days. So let me start by saying that there is little doubt that linear algebra has been heavily connected with data science. As a matter of fact, think of prototypical research problems in linear algebra and numerical analysis, like least squares regression. This has been around for over 200 years, since the time of Gauss, basically. You're trying to fit observations in order to figure out the parameters of a linear model. And of course, this is a prototypical research problem, how to solve least squares regression problems efficiently. This is a prototypical research problem in numerical analysis in matrix computations. How to solve it efficiently, how to solve it robustly, how to solve it in a numerically stable manner. Another very fundamental problem in matrix computations has to do with principal components analysis. Now, principal components analysis is a statistical technique. I think of it as dimensionality reduction. You have data living in a high dimensional space. You want to look at low rank approximations because you want to interpret the principal components. You want to maybe just plot them or say something about their behavior and their connection to the physical system generating the data. In numerical linear algebra, to compute those principal components, you are doing things like the singular value decomposition or eigendecompositions of covariance matrices. And again, another prototypical research problem that has been around for well over a century, early 1900s. What has not been around for such a long time is the connection between numerical linear algebra and randomization, which is a topic that if you are a theoretical computer scientist, you know very well. Randomization and sampling are a resource in theoretical computer science. They allow us to design provably accurate algorithms for problems that are either massive or computationally expensive. The history of randomized algorithms is fairly long, goes back at least to the 1970s, let's say, when randomized algorithms for primality testing came out. And there are thousands and thousands of papers in the theoretical computer science literature discussing randomized algorithms for many problems. The typical uses, as I said, we're talking about problems that are massive. In terms of matrices, what could this mean? Well, this could mean problems that are dealing with matrices that are, let's say, in the many tera or peta scale. So matrices that you cannot really easily store. You certainly don't want to store them in random access memory close to the CPU because you cannot fit them there. So instead of working with these matrices, a potential alternative is to work with just a sketch of those matrices. And this is probably something that, you know, in traditional numerical linear algebra matrix computation textbooks, you are not going to see a lot of that. They deal mostly with exact computations. The other thing you are going to want to use randomized algorithms for is for problems that are computationally expensive or even NP-hard. And again, you can read your favorite matrix computation textbook and you probably won't find the word NP-hard there. The reason is that most of the matrix problems we are used in seeing, things like, you know, least squares regression, SVDs, matrix multiplication, of course, kind of the prototypical simplest problem, they are all polynomial time solvable. So you can solve all of them in pretty much order n cube time. And more expensive problems in linear algebra hardly used to appear. However, as linear algebraic matrix computation algorithms become the workhorse behind data science and big data, other problems that were not kind of traditional matrix computation problems have emerged that are computationally really expensive and NP-hard, as a matter of fact. For example, you start seeing combinatorial optimization problems such as the so-called column subset selection problem. You are given a matrix, let's say that the rows of the matrix correspond to objects, the columns correspond to features. You want to pick a set of representative features from your data. And this turns out to be a combinatorial optimization problem. You want to pick k out of n columns, there are n choose k choices, and how do you solve this faster than, of course, brute force? Or you might want to design a corset, a set of representative objects, for example. then again this problem becomes computationally expensive. And you want to design approximation algorithms for these problems. Or sparse PCA, where you enforce a sparsity constraint on your eigenvectors, if you will. Instead of just asking the question of let's get the exact eigenvectors or singular vectors, let's also force them to be sparse. Now that becomes hard. You could have sparse approximations where you basically regularize, let's say, under constraint least squares regression to have a sparse solution. That problem is computationally expensive. K-means, it's not a traditional numerical linear algebra problem, but it has a very nice linear algebraic formulation using projection matrices of a special type. And this problem is NP-hard again. So there are lots of questions that are not included in traditional matrix computation textbooks, but at this point they probably should start being included, and they are difficult to solve. They're NP-hard. Randomized algorithms are useful in this setting. Sort of in a nutshell, I'm going to start with a prototypical problem. I'm looking for matrix multiplication, how to speed it up through randomized algorithms, let's say. And a very, very easy construction. This is not the only way to think about this problem, but this is kind of visually, I think, the most appealing. You have the matrices A and B, and instead of working and multiplying out the full matrices A and B, you keep a few columns from A, you form this matrix C, a few rows from B, you form this matrix R, and you multiply out C and R instead of multiplying out A and B. So this is a very simple approach. It has been around since, I believe, 1998, a Fox paper by Ravi and Santos Venkata and Alan Fries. A very simple approach. And an important topic here is how do you pick the columns and the rows that you are going to keep. And I remember I was a graduate student at the time doing my PhD actually with Ravi, and he said that not all columns are equal, right? Because what if you have a single non-zero column? You want to keep that column. This is the only informative column you pretty much have in your matrix. So you're going to need to design a probability distribution. We'll see that in a minute, a very simple probability distribution that sort of focuses on keeping and sampling the important columns, if you will. And then about 10, 12 years ago at this point, another idea came out, and that was sort of, I think, a breakthrough idea. The breakthrough idea was really simple. By preprocessing the matrix, if you have a matrix whose information is focused on just a few elements or a few rows or a few columns, but you preprocess it appropriately. So multiplying it by, let's say, a random sign matrix or a random Gaussian matrix, you disperse all this information. You basically spread it out. You make all the columns, all the rows, all the elements almost equally important. And now you can do uniform sampling. So really two different choices here. You either look at the matrix and design a probability distribution that respects the structure in the matrix, or you wash out the structure in the matrix by pre or post multiplying by these random projection type matrices that I'll talk a little bit about later in the talk. This is the matrix sketching part. So you start with your matrix, you create a sketch of the matrix, you operate on the sketch. The matrix perturbation theory part, which is deterministic, comes next. And this matrix perturbation theory part says that if your sketch is close to the original matrix in a well-defined sense, typically they are close with respect to some matrix norm, typically a unitarily invariant norm as well, then the small matrix, the sketch, is close to the original matrix in terms of other quantities as well. Singular vectors behave similarly, singular values are close to each other, so spectral properties, if you will. So this is the rough outline of randomized algorithms applied in numerical linear algebra. You sketch by sampling or by sketching in other ways using those random projection matrices. Then you apply the matrix perturbation theory ideas which allow you to say something about the behavior of the sketch compared to the behavior of the original matrix. The area has been fairly interdisciplinary by design and by necessity. So you are looking at theoretical computer science to get motivation for randomized and approximation algorithms. Many people in this room have been trained in this area. You also need a lot of background from numerical linear algebra, things like matrix computations, of course. You need to know how the standard algorithms operate. You call the standard algorithms in many cases on the sketch. Perturbation theory, of course, and from perturbation theory, the area has used just, very elementary results, if you will. So far at least. And then another area of applied mathematics which benefited, I think, from randomization numerical linear algebra, but also benefited randomization numerical linear algebra as well, it has been a very nice symbiotic relationship, was the part of probability theory that deals with measure concentration results on sums of random matrices. And Joel is here, and he's written one of the definitive textbooks on the topic. the idea here is that you are looking at sums of random matrices, so random variables that are now matrices as opposed to just being numbers, and you want to say something about their behavior. And there are now matrix Hefting, matrix Bernstein, matrix Chernoff inequalities, just like there have been Bernstein, Hefting, and Chernoff inequalities for sums of random variables. And I'm going to use actually something that Joel said. This democratized the field. It makes the field easier, and a lot of the proofs are now sufficiently easy that you can present to graduate students, if you will. Proving the actual Chernoff matrix, the matrix Chernoff, Hefting, and whatever Bernstein bounds, that might not be so easy, but given those bounds, a lot of the results in the Randall-Lay community have become easy to prove. This, I like to think of this as the prototypical Kalum-Ross sampling algorithm. Here's one way to think about this. You are given the matrix, you are given probabilities pi over the columns, they sum up to 1. You do IID trials because that makes life easier. It's easier to analyze when you have independence. And in C trials, you keep C columns of A to include in this matrix C. And that's your sketch. One thing you need to do often is to rescale. So you need, in certain problems in particular, to rescale the columns that you keep, and you rescale them to account for the columns that you are not picking. And this makes your estimators eventually unbiased. We're going to see such an example in the very next slide. So really simple ideas. This is, at least for me, one of the appeals of the area. Just sample columns of A in IID trials with respect to some probabilities. Let's see what these probabilities could be. I'm going to use this sketch, just a sample of the columns, to approximate AA transpose. So kind of the simplest program. This is a Gram matrix, a covariance matrix, if you will, and you are looking to approximate AA transpose by just CC transpose. This is a column sample. M by N, the original matrix, M by C, with C much smaller than N, of course, is the sketch. And the question is, what are good probabilities? And these probabilities have been known for about 20 years now. Let's keep columns of A with probability proportional to their Euclidean norms squared. So really simple stuff. Columns that contain larger entries are retained with higher probability. To an extreme, think of a single column of all ones, everything else is 0 in matrix A, then you're definitely going to keep the column that has non-zero entries, which is what you'd like to do. So this very simple probability distribution, I'm using this MATLAB notation here to denote the ith column of the matrix, works. There are other ways to view this particular setting, let me say. You can view the product AA transpose as a sum of rank 1 matrices, and actually this is the better way to apply the matrix Bernstein inequalities, but that's fine, that's less important here. Let me give you a way that I like to think of this sampling procedure, which is going to connect it also to different sketching methods based on random projections. So the way I like to think of this sampling procedure is as multiplying the matrix A by a sampling matrix S to create the matrix C. So the sampling matrix, if you've never seen it, you are not going to just follow from this two-line description. You're going to need to do some thinking on your own. But the sampling matrix is just an N by C matrix, single non-zero entry per column, indicating which column was picked at one of those C independent identically distributed trials that you are doing. So N by C matrix, you multiply A by this N by C matrix S, you end up with a column sketch. So C, the column sketch in this case, contains exactly C columns of the original matrix. But this particular representation with this matrix S, what I want to highlight, it's exactly equivalent to the algorithm I described, is that S is extremely sparse. It has a single non-zero entry per column, overall exactly C non-zero entries. They're equal to the rescaling factors if you are doing rescaling, but still the sparsity it's extremely sparse. And an obvious question here, which we'll discuss, is why don't we use a dense matrix instead of a sparse matrix to create a sketch? And indeed, you can do that. If you do the sparse matrix, you are doing column sampling. If you want to do the dense matrix, you are going to be doing sketching in different ways. Let me give you a result. This is a result you can assign to graduate students as a homework if they know what the Frobenius norm is in randomized algorithms. It's a very elementary result. It says that you can get an error bound for the Frobenius norm. The Frobenius norm square of a matrix is the sum of the squares of its entries. So this is sort of an entry-wise average error, if you will. And what you are looking at here is that if you sample enough, if you sample Frobenius norm A to the fourth, that's a large value, but it is what it is, divided by epsilon square, epsilon is your accuracy, times the logarithm of the failure probability of 1 over the failure probability, you're going to get a bound like this. You're going to get that AA transpose minus CC transpose, the Frobenius norm is less than or equal to epsilon. And this is a simple proof based heavily on the fact that CC transpose, element-wise, is an unbiased estimator for AA transpose. So in an element-wise sense, the expectation of CC transpose is equal to AA transpose, and then you can also bound the variance, and this goes through elementary arguments. If you want to get the high probability result, there is a martingale argument as well, but it's not a matrix martingale argument. It's just a standard martingale argument, which is why I say that this is a relatively straightforward result that graduate students can solve as a homework in a randomized algorithms class. This is not so straightforward. So now we change the norms. We're looking at the 2-norm bound. This is the largest singular value of the matrix difference. That's what the 2-norm is. So now you are looking for the same exact bound. I have to have the extra assumption here that the specular norm of A is at most 1 to make the two bounds comparable. That's less important. Notice the difference in the bounds. We moved from a dependency on the Frobenius norm of A to the fourth. We moved to a dependency on the Frobenius norm of A square. So this goes down. So the sampling complexity here is smaller. The other Frobenius norm square moves inside the logarithm, which is pretty nice. So it's a smaller dependency for sure. You can get the same bound. This proof, I think the first proof of this fact appeared in a paper by Mark Rudelson and Roman Vysenin, went through the Khinchin's inequality that was involved, but it has eventually become much, much simpler. So at this point you can prove this using a matrix Bernstein inequality. Assuming you know the matrix Bernstein inequality, you can prove this in under a page. So this has become a simple thing to prove given measure concentration results for some of random matrices. And this has opened up a lot of questions on how to bound the spectral norm of random matrices. This is a random matrix, AA transpose minus CC transpose. There are lots of methods. And in cases where, in some cases, you can just bound it by upper bounding by the Frobenius norm. The Frobenius norm is always an upper bound for the 2 norm, typically easier to bound. So you can do that. You can use matrix concentration inequalities. You can use the moments method. This goes back to the time of Wigner. You can use the entropy concentration method, which I would say was devised by Mark Rudelson and Roman Vysenin, but was also implicit in the paper by Ken Clarkson and David Woodruff a few years ago on sparsity preserving random projections. You can use Khinchin's inequality and a number of other tools. So this has been a nice area actually to work on at the interface between theoretical computer science and applied mathematics and probability theory. There are even matrix martingale arguments at this point. I think Rasmus King had a couple of those results. Let me say that the logarithm here is kind of necessary. This is from coupon collector. You're not going to get around. You cannot remove it with randomized methods. You can remove it with deterministic methods, at least in some special cases, at the expense of the increased computational cost though. So let me get back to the question of, you approximate the product AA transpose using CC transpose. And remember that I like to think of C as A times S, where S is a sampling matrix that is extremely sparse. What if you replace it by a dense matrix? You can do it. So let's replace S by a random sign matrix, plus minus 1 up to rescaling with probability half. You'll get very similar results. So this is coming from a paper by Avner, Magin, and Tasso Zouzias. And the structure is basically the same. This is a 2-norm bound. The same factors appear here. So the structure is the same. It's not obvious what the benefit is. And let me tell you what the benefit is. The benefit is that if you're doing sampling, you are not oblivious to the input data. Your sampling probability depends on the input. However, the random sign matrix construction, of course, is oblivious to the input. You don't need to construct, to look in the input matrix to construct your sketching matrix at all if you are doing a random sign matrix. This is not a particularly good choice, though, because it's expensive to multiply a matrix, say, by a random sign matrix, but much better choices are known. And let me just say that, you can look, for example, at the paper by Ken and David in 2013, who basically said that there is actually a very nice construction for S, which is input sparsity time preserving. So if your original input matrix is sparse, you can apply it in time that is essentially proportional to the sparsity of the input matrix. Has been analyzed in a number of different ways. The original proof, at least in my mind, is very reminiscent of this entropy concentration method I talked about. Michael and Zhangri had a paper where they analyzed it by upper bounding the 2 norm by the Frobenius norm. So yet another method. And then Jelani, Nelson, and Hui had a paper where they analyzed it and they gave the tightest bounds, as far as I can tell, for a variant of this construction, where they analyzed it using the moments method, where they look at the trace of a power of the matrix and they upper bound the largest singular value, the 2 norm, by using that trace. So this is a nice case study actually to see different methods in action. Why is randomized matrix multiplication so important? Because a lot of other problems that we care about reduce to randomized matrix multiplication. For example, least squares problems over constrained ones. So you have a tall and thin matrix A, you have a vector that you are looking to figure out, this X opt you are trying to figure out, you have your response vector B. So design matrix A, response vector B, you're trying to minimize B minus AX. Let's say this optimal solution is X opt. Well-known problem, we know of course how to solve it. You never want to use Cholesky decomposition because this squares the condition number, it's very numerically unstable. QR decomposition or the SVD are the appropriate methods. They all have the same complexity from a theoretical perspective, big O notation, the constant factors increase as you go down the list. Fine. An approach to solve this problem in the randomized linear algebra community would be to say, well, I'm not going to work with A, I'm not going to work with B, I'm going to work with sketches of A and B. What are the sketches? Pre-multiply A and B by S. This random sketching matrix, it could be a sketching matrix, it could be a sampling matrix. If it's a sampling matrix, then you are sampling rows of A and the corresponding elements of B, and you are solving the smaller problem. So that's why I like to think of this sampling sketching matrix S, because in this case it makes the story very clear. Instead of working with A and B, I work with S times A or and S times B, and this is just a smaller problem. Could be sampling again, could be sketching, depending on the application that you have in mind. And here are typical results that you are going to get. If this is a sampling matrix, so you keep a few rows of A, the corresponding elements of B, you solve this smaller problem instead of solving the original problem, and you get some solution, let's call it X tilde opt. You plug it back into the original problem, so you look at B minus AX tilde opt. This cannot be better than the optimal solution, you are never going to beat this, but you are not going to be much worse either. So you're going to be 1 plus epsilon closed, that's a relative error bound, constant failure probability, all these things can be modified as you see fit. How many rows do you need to keep for that? Just d over epsilon plus d log d. So this is the sampling complexity, the target sampling complexity for this particular result. And the one interesting thing here is that the sampling probabilities are not going to be row lengths of A or something like that. They're going to be unfortunately more involved. You're going to need to look at the thin SVD of A, which has this matrix U here. Thin SVD means I only show you the singular vectors corresponding to non-zero singular values. So this is an n by d matrix. The columns of this matrix are pairwise orthogonal and normal. There is not much I can say about the rows, except that the Euclidean norm is between 0 and 1. It is the row norms of this matrix that you're going to have to look at to form sampling probabilities for these over-constrained least squares problems. These have a name in statistics, they're called the leverage scores, they're used for outlier detection, but in the context of randomized linear algebra, they reveal to you where the true action lies in the design matrix. They tell you which observations are more important than others. If you sample with these probabilities, you're going to get the influential observations. How to compute leverage scores, again a topic where quite a bit of research has been done. There is an obvious algorithm through the SVD that's expensive, but there are randomized algorithms that get you relative error approximations for all the leverage scores in times like this. And if you apply ideas from Ken's and David's paper, you can replace this ND factor here, which is the dimensions of the input, which are the dimensions of the input matrix, by the sparsity of the input matrix, as a matter of fact, roughly speaking. And there is a very nice idea due to Michael and Chris and Cameron Musco, the ridge leverage scores, a very nice generalization of the leverage scores with many desirable properties. I'm not going to talk more about this. Let me say a couple of words about the connections with matrix multiplication. If you look at this result, at the very heart of the result, you can actually prove that for any matrices, sketching, sampling doesn't matter. As long as those two conditions, I'll talk about them briefly, are satisfied, then you can get the kind of error that I promised. So all you need is your sampling or sketching matrix to satisfy those two conditions. Both conditions are randomized matrix multiplication. So you have U transpose U. U is the matrix of the left singular vectors of A. You are approximating it by using randomized or sketch-based or whatever matrix multiplication. As long as this error is nicely bounded, you're good to go. And then you're approximating the product U transpose times B perp, that's the part of B that lies outside the column space of A. In exact arithmetic, this is equal to 0, but if you're doing a randomized algorithm to approximate it, it's going to be non-zero. As long as you can bound those two quantities, and this can be just bounded directly by randomized matrix multiplication if you have a random construction for S, you're good to go. And indeed, that's a good proof strategy if you want to construct a new sketching matrix or something else that solves the over-constrained least squares problem by sampling. And there has been a lot of follow-up work. Chaim is here, and 8 years ago at this point, they designed BlenderPick. They used the sketch as a preconditioner in iterative algorithms. There has been work on other norms, not just L2 norm regression. Ken and David had their paper on input sparsity preserving projection. A lot of work on other ideas actually coming also from here at Berkeley on other iterative sketching-based methods and the so-called Hessian sketch. Michael is going to be here and he's going to talk about adaptive and volume sampling approaches to do, again, regression problems. The papers I mentioned, Michael and the Musko brothers had work on ridge leverage scores and many others. And if you care about the other case, so I talked about over-constraint, if you care about under-constraint, you can definitely look at a paper of ours last year at ICML, which overviews prior work and also gives an iterative method to solve such problems. And the square case is very interesting. So I talked about under constraint, mentioned something about, I talked about over constraint, I mentioned something about under constraint. The square case is also very different, very interesting. Special case there, Laplacian solvers. This is work by Dan Spielman and Sen-Hua Teng. It was pioneered by them. And we have Yannis Koutis is here and Richard Peng is here, so I'm not going to talk much about this at all. I'll delegate to them. The other prototypical problem, and yeah, let me take a few minutes to talk about this. The other prototypical problem is SVD, the singular value decomposition. And I like to think of this problem in terms of the Krylov subspace. And now the Krylov subspace is, again, a word you probably won't find in your favorite theoretical computer science textbook. It's this space here. For a matrix A, sketching matrix S, you form this space, which basically just multiplies the original sketch by A transpose. And it's known that this particular Krylov subspace contains good approximations to the top K, in this case left singular vectors of A. Why and how, that's a different story, but I think one thing I'd like to highlight is that this is sort of without worrying about numerical stability and all kinds of issues that you have to worry about. Lanczos methods have been designed in particular to operate on this particular, on this space and extract approximations to the left singular vectors of A in a numerically efficient, numerically robust way. The early approaches for SVD in the randomized linear algebra community looked at just AS. So the first entry of the Krylov subspace, just one sketch, and even based on that one sketch, they were able to get relative error approximations for the Frobenius norm. Again, don't read everything here. The only thing I want to highlight is that we could get low rank approximations, nice low rank approximations to the original matrix A by just looking at AS. And then eventually, the next family of algorithms that were analyzed, and these were in a paper by Joel, Gunnar, Halko, and I think Rocklin and Tigert had the results on that at the same time, looked at the last entry, this subspace iteration. So just the very last entry, and with that you're going to get relative error approximations for the 2 norm as well, which before we didn't know how to get if we looked only at the first element. And then, of course, eventually, and much of this, at least in my mind, I was influenced in this presentation by work by Chris and Cameron Musko in NIPS a few years back. You look at the full Krylov subspace. I don't worry about numerical issues. Let's assume I can come up with nice ways to extract good left singular vectors from this subspace here. And it turns out that all these 3 methods can basically be connected to randomized matrix multiplication. I'm not going to discuss this result in any kind of detail. Let me say that assuming singular value gaps, a gap between the kth and the k plus first singular value, you can get nice results for Q. How many iterates do you actually need to get good approximations? The kind of results you are going to get, just to show you one result here, the kind of results you're going to get are going to be relative error approximations for both the Frobenius and the 2 norm. The value of Q is going to depend on the logarithm of the rank of the input matrix A over epsilon, that's the target accuracy, which is pretty nice. So these are hidden in the logarithm, divided by the square root of the gap between the k and the k plus first singular value. happy to discuss details offline. Let me just say one word about element-wise stuff. One thing I didn't talk about at all, I talked about sampling rows and columns. I talked about sketching input matrices using random projection ideas, but you can also sample elements. So you can take your original matrix A and keep a few elements only. Zero out everything else. And that's still a nice sketch. The probabilities, this is pioneered by Dimitris Achliopoulos and Frank Maxeri. Matrix completion is connected. It basically says that you can reconstruct from element-wise samples any matrix as long as it has exact low rank and some assumptions on the so-called incoherence, which is a version of the leverage scores. The sampling probabilities you are going to get, you want to sample with probabilities that depend on the square of the entry plus the absolute value of the entry. And lots of, this is a linear combination of those two quantities, and various parameters for alpha here have been studied in prior work. But you want both of them because this is going to deal better with small entries. You cannot just do Aij square. There are structural results here as well. I'm going to skip matrix completion. Let me just, one thing, there is a version of leverage scores for elements as well. There are element-wise leverage scores, and perhaps not surprisingly, they are the sum of the column and row leverage score for that particular entry. Okay. So, this is what we're going to be talking about to a large extent this week. Randomization and sampling as a resource to solve problems in matrix computations. You can carefully sample rows, columns, elements of a matrix and construct sketches. Leverage scores come into play here, or you can pre-process the matrix by using random projection type matrices, and then you can be a lot less careful in sampling. You can basically do uniform sampling. I was sparse in references partly because there are now a number of reviews. Gunnar and Joel and Nate had one of the first reviews. Michael, David has a very nice book on sketching as a tool for numerical linear algebra, and Michael and I had lecture notes and an article in CACM as well that I would invite you to take a look at. So thank you very much for your time, and I guess let's not take questions and move on to the next speaker. Okay? Thank you. So I'm going to introduce the next speaker, Ilse Ipsen.